Hello and welcome to your background video for the Acids and Base Solutions Lab. During this week's lab, we will be learning about several different definitions of acids and bases, the difference between strong and weak acids and bases, and how the concept of equilibria applies to acids and bases. There are three popular definitions of acids and bases: Arrhenius, Bronsted-Lowry, and Lewis. An Arrhenius base is defined as a substance that produces hydroxide ions in solution, and an Arrhenius acid will dissociate to produce hydrogen ions in solution. There are lots of examples of Arrhenius acids and bases. Hydrochloric acid, or HCl, is a common Arrhenius acid. If you look at the reaction of hydrochloric acid with water, you see that the hydrochloric acid dissociates into H+ and chloride ion. Many common acids fit this definition. Typically, you can recognize them from their chemical formula because the first element in the formula is a hydrogen. A very common Arrhenius base seen in general chemistry laboratories is sodium hydroxide. When dissolved in water, sodium hydroxide dissociates into sodium ions and hydroxide ions. The presence of the hydroxide ions in solution fits our Arrhenius definition. Other soluble hydroxide salts fit the Arrhenius definition, so these are easy to recognize. The Arrhenius definition works well for some acids and bases, like hydrochloric acid and sodium hydroxide, but it doesn't explain how something like ammonia is able to turn a solution basic. So a better, more inclusive theory is necessary. Ammonia is not an Arrhenius base, but solutions of ammonia are basic because it accepts a proton from water to form ammonium. The loss of the proton from the water leaves hydroxide, which causes the solution to be basic. Still, we would say the ammonia acted as a base in this situation because it accepted the proton. The recognition that the ammonia accepted the proton and that the water donated the hydrogen ion is the key chemical behavior that led to a better, more inclusive theory. This theory is credited to Bronsted and Lowry and is appropriately called the Bronsted-Lowry theory. In the Bronsted-Lowry theory, water is a special molecule. It is an amphoteric substance, which means it can actually act as either an acid or a base. In the Bronsted-Lowry definition, we see that this behavior is very important. In the ammonia reaction, the water donated a proton to the base, which matches the definition of an acid. And the water acted as a base when we place hydrochloric acid in it. The water accepts the proton donated by the hydrochloric acid, which matches the definition of a base, and the hydrochloric acid is an acid because it donated the proton. In this class, the Bronsted-Lowry theory will be used the most. Restated again, this theory states that an acid is a hydrogen ion or a proton donor, and that a base is a proton acceptor. Finally, there is a much broader acid-base theory. Lewis theory states that an acid is an electron pair acceptor and a base is an electron pair donor. As a broader theory, it is useful when the transfer of the proton is not the reason for the acid-base behavior. The proton transfer is still accurately described by Lewis theory, but Lewis theory explains many more situations. However, in today's laboratory, the acid-base properties can be described by either Arrhenius or Bronsted-Lowry theories. Thus, consider the chemical formula of each substance and the observed pH values to draw conclusions about the acid-base properties. Even with our definitions, not all acids and bases have the same strength. Strength is a funny word. In everyday life, it means how much we can lift or do. However, it doesn't actually mean that when referring to acids and bases. Strength is a word associated with how much the acid or base dissociates in water. A strong acid or base will completely dissociate when placed in water. Here are some examples of strong acids, and here are some examples of strong bases. You can see in each of these that the reaction is written with a single arrow. This means that all of the acid or base in the solution dissociates into two ions, one of which has to be either a hydronium or a hydroxide ion. Weak acids and bases won't fully dissociate. Instead, it will partially ionize in solution. This implies that in solution, you will observe some of the molecular acid and some of the ions. Let's look at acetic acid, which is commonly abbreviated HAC. Because it doesn't fully dissociate, an equilibrium forms between the acid, the proton, and the acetate ion. We can write an equilibrium constant expression to reflect this. Just like last week, we will put products raised to their coefficients over the reactants raised to their coefficients. Instead of Kc, we can call it Ka to reflect that this is the acid ionization constant. Weak bases also will not completely dissociate. Here is the reaction of ammonia with water. An equilibrium forms between ammonia and the water and the ammonium ion and the hydroxide ion. We can express the relationship between concentrations with this equilibrium constant expression. We can call this constant K sub B to reflect that it is the base ionization constant. One of the purposes of this week's laboratory is to observe how the relative strength of different acids is measured. Or can we tell something about the strength of an acid simply by measuring the pH of a solution? The pH of a solution is a measure of the hydronium concentration or the proton concentration. The P in pH is an operator, which means a negative log. So pH is equal to the negative log of the hydronium ion concentration. If we had a 0.1 molar solution of an acid, we could use the equation to calculate the pH value we would expect for a strong acid. In this case, the pH value would be expected to be 1. So when we observe the pH of a solution, we can compare the measured value to the expected value and comment on the relative strength of the acid. A pH value close to 1 would indicate that the acid is a strong acid. A pH value greater than 2 would indicate that the acid is probably a weak acid. We'll be observing the pH of lots of different solutions in the laboratory this week. You will see both acids and bases. The pH scale in water typically runs from 0 to 14, but it can actually be negative for very strong acids and above 14 for very strong bases at high concentration. To interpret the scale in terms of acids and bases, we start in the middle. A pH of 7 is neutral. A pH below 7 indicates that the solution is acidic, and a pH above 7 means that the solution is basic. The final concept that we will be looking at during this lab is buffers. A buffer is a solution that resists changes in pH when small amounts of acid or bases are added to it. Your blood contains an important buffer system. It is able to maintain a narrow, healthy pH range using the bicarbonate buffer system. In this laboratory, you will simply be exploring the concept by preparing a buffer solution, then comparing its ability to resist changes to pH. You should note how the addition of a small amount of acid affects pH in both solutions. Prepare to be amazed at the buffer action. Please go watch the technique video now. It will show you how to determine the pH and collect the data you need. As always, don't forget to review your lab manual before taking your quiz.